Hello and welcome. Today we're going to be talking about an example first-order linear system. The example we're going to be talking about is the RC circuit. Okay, so let's talk about what that is. Okay, so what we're going to have is a circuit, so I'll put a node to ground there, and then there's going to be a break in the circuit, and on one side, a branch in the circuit, and on one side there'll be a capacitor with capacitance C, and that will come down here. And then on the other side of this branch, in parallel to it, we're going to have a resistor symboled by that symbol there, and it goes down. So I want to know what the voltage is, V of t, across this circuit. I'm also going to be passing through this circuit an I of t, which will pass through this resistor, but some of the current the charge will also end up on the capacitor as well. Okay. So let's talk about the current then is going to be split between the capacitor side and the resistor side as it goes across. So again, the question is, I think of I of t as a current input. Okay. And the voltage as sort of an output. Or a resulting current. A resulting voltage. Okay, so it's a voltage that's in response to this applied current, this input here. Okay, let's talk about how we set up this model. What we have is actually we have a conservation of current. So we really have what the current law, which states that I of t, if it's broken into two pieces, which I'll call IR, which is the resisted side, so we're going to have a IR on that side, and then there's also going to be this capacitive current, which we'll call IC. Like that. All right. So it turns out IR, we'll assume that this is ohmic, which means that so V equals IR, or rather, I should say this I is IR times the resistor, right? So this has a resistance R, I should say, okay, in ohms. So IR then is going to be V over R. And that's a V of t. All right, now IC, this is going to be called a capacitative current, and it turns out to be equal to dV dt times the capacitance. Okay, so that is equal to IC. All right, now let's put this together. Okay, so what we have is C times dV dt plus 1 over R, V of t here, right? And that has to be equal to I of t. All right, so clearly this is a ODE, and it's a first order linear equation. Okay, and we got it through this current law, which is the conservation of current. It means the total current that you apply has to either go through the resistor or through the capacitor. No current can be gained or lost or disappear or magically appear. All of the current that flows in has to be accounted for. That's what this means. All right, so we have a first order linear equation, and our unknown, of course, is V of t. That's what we want to find, V of t. Okay, so first of all, let's talk about a very specific I of t current. I'm going to actually apply to this current a sinusoidal current. So sine omega t, where omega is the frequency. Okay, the frequency of this applied current, so it's going to be an oscillating current. All right. So let's put all this together. Up here, we have, and what I'm going to do is multiply or divide by c everything. So what I have is a dv dt plus 1 over r times c times v is equal to sine of omega t all over c. All right, so this is a first order linear equation. Let's see if we can identify the pieces. Clearly here, that's the capital P of t from the previous video, and this is going to be the capital Q of t. All right, and how we solve this is fairly straightforward. What we're going to do is we have to take our rho of t, and that's going to be equal to e to the antiderivative of P of t dt, which is e to the t over r c. All right, so it should be noted with these resistor capacitor circuits, the parameter RC often goes by another name. We give it a name tau. And we think tau as a time constant. It's the characteristic time constant for the capacitor. Okay, so it's the time constant of the RC circuit. All right, so we have rho. I think I'm going to have to switch to a new page here. I'm going to rewrite this again, dv dt plus 1 over RC, and that's that tau constant there, times v is equal to 1 over c times sine omega t. Okay. All right, and we found our rho. Rho of t is equal to e to the t over tau. Okay, and I've replaced RC with tau there. All right, multiply everything on each side, and we get dv dt times rho of t plus 1 over tau rho of t times v equals 1 over c e to the t over tau times sine omega t. Okay, so this whole thing, we can reverse that product rule again and get rho times v. We take the derivative of the whole thing there, this product of two functions. And that's going to be, on this side, 1 over, the same thing, 1 over c e to the t over tau sine omega t. All right, so of course we anti-differentiate both sides. We always go plus, I'm going to put plus k there. All right, I'll put a dt there and an antiderivative there. And of course the antiderivative of a derivative is just the rho times v. So I'm going to go e to the t over tau times v of t is equal to k plus this thing we need to take. So I'm going to call that 1 over c, and this integral here, e to the t over tau times sine omega t dt. All right, that looks pretty good. And now we need to actually turn and figure out how to actually compute this integral, and it is actually very doable, but it does take a few steps. So, and we have to do it by parts. Okay, so let's do this by parts integral. What I'll do is take the antiderivative of e to the tau, t over tau, and take the derivative of sine. That's how I always do my computation, so I'll start here. That's how I think of doing integration by parts, I should say. Okay, so we have a tau, e to the t over tau. That's the antiderivative of this part here. And I multiply it by my sine of omega t. And I subtract it, and I get I have to put that tau out front. And now I get an integral e to the t over tau of cosine omega t. Now I'm going to put an omega outside because I took the derivative, and that's the chain rule. Okay, so we're moving along here, and now I have to contend with this integral now. All right, so let's see if I can rewrite this. Actually give myself a few more lines here. I'm going to kind of cram it in a bit. There's my tau, e to the t over tau, sine omega t, minus t over t times omega. And now I'm going to do this integral here. And I'm going to do it by parts yet again. So we get another tau, e to the t over tau, times cosine omega t, minus, and we have to go t over t times omega yet again, and we have the integral e to the t over tau times sine of omega t dt. When I take the derivative of cosine, it's actually negative sign, so that becomes a positive there. And I put that in that square bracket. Okay, so we see we've done two integration by parts now. And we've gotten back to this inside of here is this integral, but of course it looks exactly the same as the one we started with. And that's the goal. We wanted to actually compute this integral, but we actually, after two steps of integration by parts, got back to where we came from. So what we need to do is actually solve for this. This is our unknown. To solve for. So we have to isolate that unknown. Okay, so that's easy enough to do. So what I'm going to do is I'm going to bring this over to the other side. So I get integral e to the t over tau sine omega t dt is equal to all this other stuff here. So we see here, after I put it all together, I'm going to distribute this in. So I get a negative tau squared times omega e to the t over tau cosine omega t. All right. And then I also have this piece here, which is going to be just plus tau e to the t over tau sine omega t. All right, but now when I move this piece over, oops, I didn't really give myself enough room here. I should put, I'm going to do a little bit of erasing here. Just give myself a little bit more space. Put that negative sign there, put an equals there. This whole thing, there was one of these here, but then we see that there was, if I distribute this term in, I get a tau squared omega squared, and then there was a minus there. So when I add it to it, I'm actually going to get a factor that's 1 plus tau omega quantity squared. And I'm sorry, I should have made that bigger. But the idea is we're going to divide that through e to the t over tau sine omega t dt, and that's going to be equal to then 1 over 1 plus tau omega quantity squared all times negative tau squared omega. Actually, I'm just going to do a little simplification here. I'm going to put a tau there, and then I'm going to have a negative tau omega cosine omega t plus sine omega t. And then I all multiply by e to the t over tau. All right, so that's the value of that integral. Okay, so now I'm going to go up here, see if I can finish this out. Okay, so we know that this integral that I just computed here, now I can put this all together by multiplying by this whole thing here by e to the negative t over tau. And that's going to cancel things. So what I'm going to get is a v of t is equal to k, that integrating constant, e to the negative t over tau, plus 1 over c times tau 1 plus tau omega quantity squared times negative tau omega cosine omega t plus sine omega t. I hope you can read that. I'll put it on the next page. Okay, so that's our solution. All right, let's now put that on the next page. So our solution, we're going to get v of t is equal to k e to the negative t over tau plus tau over c times 1 plus tau over times omega quantity squared, all times tau omega cosine, that's a negative tau omega cosine, omega t plus sine omega t. Okay, so that's a very acceptable answer. Let's see if we can kind of see two parts to it. First, this is a decaying, or sort of what I call the transient piece. Okay, and of course it goes to 0 as t goes to infinity. As it gets large, it decays away. The other part, though, represents the steady state, or I should say, yeah, the steady state. Response to input current. Okay, so that's the steady state response to the input current right there. Okay, so really what I'm interested in is actually this piece right there. I want to know more about it. All right, so let's look at this. I'm going to call it VSS of t is just this piece right here. And I want to know more about it. And what you can really see is actually there's a cosine term and a sine term, right? And what I'm going to do is rewrite it a little bit. What I'd really like to know, the question I have for this is, what's the amplitude of the voltage? So what's the amplitude of the voltage? So we see that it's oscillating, and it's oscillating with the same frequency as the input. It's both omega there at that same frequency, but I want to know the amplitude. So what I'm going to do is actually kind of see if I can get a little perspective here, and look at this as an A omega times the cosine omega t plus B omega times the sine omega t. All right, so we can see it's of this form where A omega is going to be tau over c negative tau squared times omega over c times 1 plus tau omega quantity squared. All right, and B of omega is going to be simply tau over c times 1 over 1 plus tau omega quantity squared. Okay, all right, so those are the two pieces. So how are we going to get a better idea? So we're going to actually use a trig identity. So recall that sine A plus B, right? So those are any two angles. Is equal to sine A times cosine B plus sine, apologies there, cosine A times sine of B. Okay, so that's going to be very useful here because I see I have a cosine B and a sine B. So B in this case can be my omega t, right? And then this term right here, that's what I'm going to call my A omega. And this term here, or that factor I should say, is going to be my B omega. All right. So anytime I see this type of expression, I can express it this way. So now my voltage of T is I can relate it in this way. All right. So we want to see if we can understand a little bit more about how to get at this. All right. So but we need to do a little work here because this isn't quite right because we see that sine only varies between 0 and 1 and cosine only varies between 0 and 1. So we need to do a little bit of work here to get it in the form. And so it turns out if I rewrite it as if I write it as follows, if I write a squared plus b squared, all multiplied by a over root a squared plus b squared times cosine omega t plus b over root a squared plus b squared times sine omega t. Then this term here and that term there can be my sine A and my cosine A. All right, and these now, of course, vary between 0 and 1, and if you sum the squares of them, you get 1, which is exactly the equality. So what this represents then is an amplitude term. Right there. That's an amplitude term. So I actually can define that as such. That's going to be amplitude of omega, of the variable omega, and that's going to be root a squared omega plus b squared omega. So that's not exactly true there, but it's close. Okay, so now we have it. All right. Likewise, it begs the question then is, what is A? Well, clearly we can find it through inverting. What we know then is tangent of A is going to be equal to sine of A over cosine of A, which is going to be equal to, of course, A omega over B omega. So of course, if we see that if I put this in its place and that's its place, the square roots will cancel and I'll just get an A omega over B omega. Therefore, or I should say therefore, A is going to be equal to the tangent, the inverse tangent of A over B. Okay, and we may have to add some sort of angle to this depending on how it on whether or not the angle is bigger than plus or minus 90 degrees. Okay, so let's now those represent this A represents a phase shift. Of the system, and that of course represents that amplitude. So let's see if we can put this all together, and I'll put this on a different page now. Okay, so what we're going to have here then is we have our V of t is equal to this A omega times cosine omega t plus B omega times sine omega t. And that's going to be equal to, through this trig identity, this amplitude of omega times sine times omega t plus this phase shift A, okay? And the amplitude omega is going to be equal to square root of A squared plus B squared. Let's calculate this first. So recall that A omega was equal to um, negative tau squared omega all over C 1 plus tau omega quantity squared. Okay, that looks good. And B omega was equal to tau over C 1 plus tau omega quantity squared. Okay, so when we put this all together, one finds that what you get out of it is the denominators, of course, because the denominators are the same in both of these, they pass right through the sum of squares and square root, and you get back out C 1 plus tau omega quantity squared, all right, times, and what you see in the numerators is you can pull out a tau, and then you get a square root of, and what's left over is 1 plus tau omega quantity squared. All right, so we can simplify this even further and see that that, of course, term right there is the same as that. So what we get is tau over C times 1 over root 1 plus tau omega squared. All right, so that's the amplitude that results from the signal. So now let's see if we can find that phase. All right, so again, A is equal to the inverse tangent of the ratio of these two things. So capital A over capital B. Oh, oops. So if I remember, the denominators again will cancel when I take the ratio of them. So what I'm left with is simply it's going to be negative tau squared times omega over tau, which is going to be the tangent inverse of a negative tau omega, which I can write as negative, because tangent is an odd function, and so is inverse tangent. I can pass the negative right through. So that represents what I call this phase shift. Okay, so phase shift is right there. That's that A value. And again, our voltage that we're interested in is this. Right, so remember again our input. It was the input current was just sine omega t. And now our output is going to be this amplitude. That's our I of t. And our output amplitude then is going to be related to the input as follows. It's going to be tau over C, 1 over root 1 plus tau omega quantity squared times sine of omega t. But then we're going to get this phase shift minus tangent inverse tau omega. All right, so we see that because of that negative sign, we really are talking about a delay. And that makes sense if we think about our circuit again. What we have here, so we have this resistor, we have a capacitor, and if I pass current through it, and it's oscillating back and forth, like that at some frequency, some of the current is going to get sloshed onto this capacitor and get held for a little while. And some of it's going to pass through the resistor. And the resulting voltage due to this holding the current on this this capacitor versus flowing through the resistor will cause the voltage to, again, it's going to oscillate at the same frequency here, but there's going to be a delay in the response of the voltage compared to the input here, okay? So we expect there'll be a delay because of that. And also we see that the amplitude is going to depend critically on the frequency and on the tau, the constant of the circuit. Remember that tau is equal to R times C. So the bigger the capacitor or the bigger the resistor, they're both going to dampen the amplitude of this thing. The amplitude will get smaller and smaller if I change any of these constants. All right, so what we want to do now is get a clearer picture of what this looks like. And so actually I went out and plotted this. So what I did is and this is called a Bode plot. That's a guy's name, so I should put, and what you do on a Bode plot is have an omega, and it's actually two plots put together. So one, it's your phase, A, and the other one, it's the amplitude. And you can see clearly here that this is going to be a function that kind of goes like that. And because this is an inverse tangent, it's also going to look a little like this. It'll decrease down. Okay, and it's always going to be negative. And if I put omega equals 0 in there, of course it'll be 0. All right, so let's get a better picture of it. I've actually plotted the real thing for you, so I'm going to pull that up. Okay, so there it is. I hope you guys can see this. What we have here is this amplitude plot. So right here, omega, this is in radians per second, and this is just going to be some unitless amplitude of voltage. So you see here, if I have a very, very low frequency, the amplitude is going to be, I'm going to get 100% amplitude out of the thing. But as I increase the frequency up to 2 radians per second, I'm almost at half the amplitude. So my voltage can't seem to respond fast enough to this oscillating frequency. Now, when I go to 4, you see I've almost gone down to about 25% of the original amplitude. Now, if I go 6, 7, 8, and 10, I'm getting down into just maybe even a tenth of the amplitude of the original input current's amplitude. So we see that as the frequency gets higher, amplitude decays. Okay, the same thing with the phase shift. What's happening here? The delay. If omega is very small, I got 0 delay. So the oscillating frequency, it's a very slow frequency. It's going to be very small for a little omega right about there. And there's very little delay, and that's because the voltage can track the input current very, very successfully. But you see that there's a bigger and bigger and bigger and bigger delay, up to about 1.5 radians as we go further and further and further to higher and higher frequencies. All right, so here's an example of what I'm talking about. So this is omega equals 2. So that's about right there. I should be about half the amplitude. And I should have about 1 radian, maybe a little less than a radian delay. Okay, so here is I. The blue is that input current. You see it's just a sinusoidal oscillation there. That's that input current right there. Okay, and now what's here is the output voltage. All right, do you see it crests and it gets almost to just about half the original amplitude, but also doesn't rise as fast. While the current rose and hit its peak at pi over at this point right here, I shouldn't say pi over 2, but it hit its peak right about there at about 1/4 of a second. The signal it's going to actually hit its peak well afterwards, and that's because there's that delay. So we see both amplitude has been diminished because this capacitor is soaking up that current and holding it for a little while before it gives it back to the resistor. And then and it's also delayed, so it's actually holding it and delaying the eventual peak of voltage due to the current. So this is an example of a Bode plot here, an amplitude phase shift double plot. And here is in the time domain here. As you go forward and for various seconds, you can see here just oscillated up and down and the delay. So hopefully that gets a clearer picture of how the RC circuit functions when you give it a sinusoidal input current. And it also gives a good example of how first-order differential equations can describe a whole lot of applied things, including these circuits, these RC circuits. All right, thank you very much.